I got positive with COVID. Now I have somewhat recovered from that. So now we will continue the class. I do not know whether are you remembering what we have seen some 1 week before? What are the things we have seen? Anybody can summarize? Yes, yes, very good. Yeah. Yes, yes. Very good. Yes, yes, very good. Yes, yes. Nice. Yes. So working principle we have already seen that the current carrying conductor placed in a magnetic field, that is the working principle of any motor, but the condition how it is achieved in induction motor, whenever you give three-phase supply which is 120-degree phase shifted in time to the three-phase winding which is 120-degree phase shifted in space, so you will get a magnetic field that is rotating in the air gap of the induction machine. So that rotating magnetic field sweeps the rotor surface. So rotor already we are having conductors. There we have the closed path. So because of Faraday's laws of electromagnetic induction, we get EMF in the conductor. Because of that, we'll get current in the conductor. So we get that condition, current carrying conductor placed in a magnetic field. The conductor experiences a force. So that is what we have seen in the last class. So now, how to say or how to understand the produced magnetic field is rotating? That is the first question. The second question is, the magnitude of the produced rotating magnetic field is always constant at every instant. The magnitude is 1.5 times of the maximum flux. So how we are getting that? The second point. The third point, the synchronous speed. It is the speed with which the magnetic field is rotating, right? So that is called a synchronous speed. So it depends upon what parameters or what is the expression for synchronous speed. Generally, the synchronous speed, it is denoted by, it is denoted by the symbol ns. It is denoted by the symbol ns, and that is the speed of the rotating magnetic field. That is the speed of the rotating magnetic field. So we have to understand all these three now. The produced magnetic field, how it is rotating, and how the magnitude is coming around 1.5 times of maximum flux, and what is the expression for the synchronous speed. That we need to understand. One by one we will understand. First we will understand how the magnetic field is rotating. While understanding that, parallelly we will understand the magnitude is 1.5 times of maximum flux. The first 2 points are highly interrelated with respect to each other. The last point, separate derivation is there. So that we will see in today's class. So this is what I told. So when a three-phase stationary winding are excited by a balanced three-phase AC supply, the resulting field produced is rotating magnetic field. Though nothing is physically rotating, the field produced is rotating in space having constant magnitude. So now to understand that, we will take a induction motor which is having a stator. This is your stator. This is your stator. So this is your stator. Okay. And this is your rotor. Okay. And stator, no, you have three-phase winding. So the red color, that is R phase, you have red color conductor. So these two will form one winding. So that is for R phase, R dash. So here the current is entering into the coil and it is coming out. So for simplicity, no, we assume only one coil, that is only one turn per phase. Okay. So for simplicity, assume one turn per phase. You have only one turn per phase. One turn means what? Two conductor, if you connected together, it forms one turn. So for one phase, this is shown in red color. This is for one phase. So you have one conductor which is placed inside this slot. You have another conductor which is placed inside this slot. And these two conductors are connected together to form one turn, that is forming phase A, or you can say it is R phase. And similarly, you have B phase. So this is your B. So let me take, this is B dash. This is another phase, B dash. And C phase. So this is C dash. Okay. So you have three-phase winding in the stator, and each three-phase winding, no, it is having only one turn. That we are assuming for simplicity, right? And the magnetic field or the magnetic flux or the magnetic flux density produced by each phase, you can say magnetic field or magnetic flux or flux density, any way you can name it, all are proportional to each other. So now we have to mark the direction of the magnetic flux or flux density produced by each phase. For example, you take R phase. Okay, you take R phase or A phase, anything you can take. That is shown in red color. If you see the direction of the current in this conductor, according to this direction of the current, the flux produced will be like this. It is clockwise direction. It is in this direction. The net resultant flux will be like this. So it is clockwise direction. So with respect to the rotor, the flux direction is like this. But here if you see, the flux direction is anti-clockwise, and the usual flux, no, the flux which cuts the rotor, that only forms the usual flux. So if you see the direction inside the rotor, this is your direction of the flux produced by this conductor. So the resultant direction magnetic field with respect to R phase or red phase, it is in this direction. You can see here. You see here. Okay. So that is denoted by BA. Here we are taking in terms of flux density, and R phase we are taking in terms of A phase. A phase or R phase, any way you can take. So this is BA. Similarly, if you see the direction of B, you see here, this is for B phase. Okay, this is for B phase. It is like this, anti-clockwise. This is clockwise. So the blue phase, the resultant flux density, it is marked like this. And similarly for C phase, the resultant flux density, it is marked like this. So if you see the resultant flux density produced by each phase, it is differing by 120 degree in phase. If you measure the angle between BA and BB, it is 120 degree. If you measure the angle between B and C, it is 120 degree. If you measure the angle between C and A, it is 120 degree. Right? And if you say the flux produced by the each winding is 120 degree, how it is produced? Only when you place the winding like that. So this winding, it is placed like this. This winding, it is placed like this. This winding, it is placed like this. So the winding, if you place in the stator 120 degree apart from each other spatially, then only the flux produced by each winding will, each phase will be 120 degree. That is what I am saying. The winding should be 120 degrees, spatially it should be distributed, and you have to give 120 degree phase shifted in time supply. So you will get the flux produced by each winding, that is also 120 degree with respect to each other. Now you assume the flux, instead of taking flux density, you take flux itself, phi A, phi B, phi C. Okay. Anyway, you can take either, you can take flux density or flux. You take flux. So phi A, phi B and phi C. And you assume phi A is varying co-sinusoidally as phi m cos omega t. And phi B, which is 120 degree phase shifted with respect to phi A, that is phi m cos omega t plus 120 degree. And phi C is phi m cos omega t minus 120 degree. Okay. So now you have one flux that is produced by A phase winding, another flux that is produced by B phase winding, and another flux produced by C phase winding. So now the net resultant flux that is contributing the useful work, right? So how to find the net resultant flux? You have to add all these three flux vectorially, right? So the resultant flux will be phi r vector, that is equal to vectorial sum of phi A, phi B and phi C. So this resultant flux only will rotate in the air gap. Pick the magnitude of 1.5 times of phi m. Now we have to see how that resultant flux is giving that rotation effect and how the magnitude is coming around 1.5 times of phi m. So for that, we have to take every instant 0 degree when omega t is equal to 0. Omega t is nothing but that is the angular rotation. Theta is nothing but omega into t. Right? So when theta is equal to 0 degree, what is happening to the resultant? When theta is equal to 30 degree, what is happening to the resultant? When theta is equal to 40 degree, what is happening to resultant? So around 360 degree, everywhere, if the direction of the resultant magnetic field, if it is changing with respect to each angle spatially, and the magnitude with respect to each instant, 0 degree if it is 1.5 times of phi m, 30 degree if it is 1.5 times of phi m, 40 degree if it is 1.5 times of phi m, each angle, if the magnitude, if you are getting around 1.5 times of phi m, then I can say the resultant flux is having the constant magnitude, which is having the magnetic field strength of 1.5 times of phi m. In order to prove that, we have to take some instant, right? First, we will take 90-degree instant, right? 0 degree I am taking with respect to this plane. So let me assume this is 0 degree. So this is 90 degree. This is 270 degree. Some instant I am taking. This is 180 degree. This is 360 degree. Right? So we will take 90 degree. Right? So when the angle theta, that is omega t, is equal to 90 degree. When theta is equal to omega t, that is equal to 90 degree. Here we are assuming the resultant flux is moving in anti-clockwise direction. Any direction you can take, but I am taking in anti-clockwise direction because this is 0 degree. I am taking this as 90 degree. It means the vector is rotating in anti-clockwise direction. So when the theta is equal to omega t, that is coming around 90 degree, what is the direction of the resultant flux and what is its magnitude, right? For that, we have to get the magnitude of each flux. When the theta is equal to 90 degree, what is the value of phi a? So this is the sinusoidal waveform. This is phi a and this is phi b. This is phi a. This is phi b. This is phi c. All are 120 degree phase shifted. Now we are taking this instant 90 degree. So this is your 90 degree. So this is your 90 degree. So when the angle is 90 degree, what is the value of phi a flux? It is 0. You just substitute in the equation. Here, omega t, no, it is 90 degree. Cos 90 is 0. Then 90 plus 120. 90 plus 120 is minus root 3 by 2 of phi m. You substitute and you calculate, you will get. Then here 90 minus 120. You will get root 3 by 2 times of phi m. Just here you can see. When 90 degree, your phi a is 0 and your phi b, so this is the value. So this is minus 0.866 is nothing but minus root 3 by 2 times of phi m. And this one is plus root 3 by 2 times of phi m. Root 3 by 2 is nothing but 0.866. So now the magnitude of phi a is 0. The magnitude of phi b is minus root 3 by 2 times of phi m. The magnitude of phi c is root 3 times of pi 2 times of phi m. If you add all the three, what is the value of the resultant flux you are getting? What is the value you are getting? Huh? No, you simply add 0 minus root 3 by 2 phi m plus root 3 by 2 times phi m. What is that you are getting? 0. Is that procedure is right? Can I add like that? That is very, very important. Don't add magnitude alone. This is AC. You have to add vectorially. To add vectorially, you have to represent this in the form of vector. I told you that any sinusoidal varying vector can be called as phasor. So this is the phasor diagram. You have to draw the phasor diagram. Right? So Now, so you have to take this direction. So this is your direction, no? So you have, this is phi A, this is phi B, phi C. So you have to take like this. So this is your phi A. Sorry. You have to take the vector now. So this is your phi A. Oh my God, it has gone. Is the slides are visible? Okay, okay. I will share it. I will share it again. Just it is the vectorial addition, that's all. You have to add the vector vectorially. So you have phi A in one direction, phi B in other direction, phi C in other direction. Phi A is 0. So no need to worry about that. You have phi B and phi C. So in order to add phi B and phi C vectorially, you extend phi B in the opposite side. Then only you can add phi B with phi C. Are you getting my point? So it's the parallelogram law of addition. So phi B becomes minus phi B. So already one minus is there. So minus minus will become plus. So you have to use that parallelogram formula. What is that parallelogram formula? Root of, yes, cos of angle between the two vector. So what is that angle between phi B and phi C? What is the angle you will get? You will get 60 degree. Am I right? Yes. So if you do that, 1 minute. I think my slides numbers are large. So that is giving problem. Size is more. So if you apply that parallelogram law of addition, so you will get a squared plus b squared. It means the root 3 by 2 times phi m whole square plus root 3 by, is that my slides are visible now? Not visible. So root of root 3 by 2 times phi m whole square plus, so minus already it has become plus. In order to add vectorially, you have changed the direction. So root 3 by 2 times of phi m whole square plus root 3 by 2 times into root 3 by 2 times phi m squared into cos of angle between these two. So I will share it. So if you do that, the resultant magnitude you will get 1.5 times of the maximum flux. Are you getting like that? Yes. So the resultant flux magnitude is nothing but it is 1.5 times of phi m. Right? So that is the magnitude. And what is the direction of the resultant magnetic field? So if you see the direction, Now it is visible? Yes, fine. So if you see the direction, what is the direction of the resultant magnetic field? The direction, if you see, it is like this. Am I right? This is the direction of the resultant magnetic field. And what is the magnitude? It is 1.5 times of phi m. This is for 90 degree. Can you do it for 270 degree? Can you tell me? 270 degree, can you tell me the magnitude? And similarly, you do it for 180 degree. Can you tell me the magnitude? Or you do for 0 degree first. If you take 0 degree, this is the point, no? So if you take 0 degree, so this is A phase and this is your B and C phase. Am I right? Am I right? Yes. So A phase is having the magnitude phi m itself. Okay. And B and C, it is having minus half phi m and minus half phi m. So you will get like this. Am I right? So this is phi m. This is minus half phi m. This is plus half phi m. You will get like this. In this case, if you find the resultant magnitude, you will get root 3 times by 2 times of phi m. Am I correct? Yes. And what is the direction of the resultant magnetic field? It is like this. Am I right? So, if you draw the direction 0 degree, what is the direction you are getting? This is the direction for 0 degree. Am I right? Yes or no? Magnitude is 1.5 times of phi m. For 90 degree, this is the direction. Am I right? This is for 90 degree. What is the magnitude? 1.5 times of phi m. For 270 degree, this is the direction. Am I right? This is for 270 degree. If you calculate the magnitude, you will get 1.5 times of phi m. For 180 degree, this will be the direction. If you calculate the magnitude, you will get 1.5 times of phi m. If you want, you can check later. Then for 360 degree, again you will get the same. This is for 360 degree. 0 and 360 will remain same. You will get 1.5 times of phi m. What do you understand from this? Yes. So, whenever you give 3-phase input, which is 120 degree time shifted, to the winding which is 120 degree spatially spaced, each phase will give you the magnetic field that is 120 degree phase shifted, and the resultant of all the 3 phases will give you the effect as if it is rotating in the air gap. Are you understanding this point? since the direction of the resultant magnetic field it is changing, then it is called as rotating magnetic field, and it is having the constant magnitude of 1.5 times of phi m. So what is the effect it is giving? You take a permanent magnet, right, that is having the magnetic flux strength of 1.5 times of maximum flux density. You rotate around the rotor of the induction motor. What is the effect you will get? The same effect you will get in this, right? So this is only sweeping the rotor conductor, and the EMF is induced in the rotor conductor. The current is flowing in the rotor conductor. You are getting the condition current carrying conductor placed in a magnetic field. So are we got the answer for first two questions? Yes or no? Yes. How to understand the magnetic field is rotating? We understood. The magnitude is constant. That also we understood, right? Whether you see this animation is visible to you, let me show the animation. My slides are moving. Are you able to see the animation? Oh, now? Okay, then I will share the slide. I have animation. Every angle, no, your resultant is rotating. So I have the animation. Now also it is not coming. Okay, then while sharing the slide, you can feel that. Okay. So now the answer for third question is remaining. What is the third question? What is the third question? The magnetic field is rotating. It is rotating at what speed? And the speed depends upon what parameters? It is rotating with synchronous speed. The speed of the rotating magnetic field is called the synchronous speed, and its magnitudes depends on what parameters. So that one we have to derive. My slides are moving or not? Moving. Now, so now let we assume ns is the synchronous speed, that is in RPM, that is revolution per minute. Okay, and the expression for ns, no, it is given as 120 f by p. That is the expression. Okay, the speed of the rotating magnetic field, it depends upon the frequency of the supply. Other words, it is called the stator frequency, because you are feeding the stator winding with the three-phase supply, which is having the frequency f, and p is the number of poles. And here in our example, the number of poles are how many? The example we have taken.
2, sir.
Yes. Each phase you have 2 poles. You understand? See here, if you see, the flux direction is like this. Okay, so this is north pole, this is south pole. This is for A phase, you have 2 poles. And similarly for B phase, you have 2 poles. Similarly for C phase, you have 2 poles. So each winding, it is forming 2 poles. Okay. So the speed of the synchronous speed, it depends upon the number of poles. Okay. For example, if the frequency is 50 hertz, that is our normal supply frequency, right? And the number of poles are 2. What is the synchronous speed? 120 F by P. What is the value? 3000? Yes. So, if you give voltages which is having the frequency 50 hertz and the stator is having 2 pole, the produced resultant rotating magnetic field will rotate with 3000 RPM. So 3000 revolution it makes per minute. That much fast it will rotate, right? So how to get that expression? So that is what I have shown here. How to get that 120 F by P? So you have to recollect your electrical angle and mechanical angle. Do you remember that electrical angle and mechanical angle that I have taught in DC machine? Yes. So what is the relationship between electrical and mechanical angle? Your electrical angle is P by 2 times of mechanical angle. Am I right? Do you remember this? Yes. So this electrical angle, that is nothing but your electrical frequency, omega E. You can simply write omega E in the place of theta E. Your mechanical angle is nothing but that is your mechanical speed. You can write omega M. Okay. Where omega E is nothing but 2 pi into F. This is radians per second. Omega E is nothing but radians per second. In terms of frequency, you can write 2 pi into F. But this omega M, that is in terms of revolution per second. Okay. In order to convert revolution per second into revolution per minute, you have to multiply this with 2 pi by 60. Okay. Omega M is nothing but 2 pi ns by 60. How to understand this? Ns, that is in terms of revolution per minute. In order to convert revolution per minute in terms of it is not revolution per second. It is also radians per second only, but measured with respect to mechanical aspect. Okay. This is also radians per second only. This is also radians per second only. This is also radians per second only. But this radians per second, it is with respect to electrical. This radians per second, it is with respect to mechanical. So the mechanical speed radians per second, if you want to have relationship with respect to revolution per minute, you have to multiply revolution per minute with 2 pi by 60. If you multiply ns by 2 pi by 60, you will get omega M in terms of radians per second. Or if you multiply this omega M by 60 by 2 pi, you will get ns. Okay. So now this omega M I can write in terms of revolution per minute like this, 2 pi ns by 60. So this side 2 pi, this side 2 pi. If you cancel, then you can get ns as 120 F by P. Okay. And this is not revolution per second. This is also radians per second. Okay. Then only your unit will match. Okay. So that is measured with respect to electrical domain. This is measured with respect to mechanical domain. So in order to convert radians per second into revolution per minute, so you have to multiply that omega m as, or in other words, I should say you have to write omega m in terms of 2 pi ns by 60. So like this only you are getting ns as 120 f by p, right? So have you got the answer for all the three questions? Yes. So you have to remember 3 points in your mind. The rotating magnetic field is rotating and the magnitude is always constant 1.5 times of phi m, and at what speed it is rotating at synchronous speed. That expression is given by 120 f by p, right? Now the next question is, fine, the rotating magnetic field is rotating at the synchronous speed. What speed the rotor of the induction motor will rotate? Any idea? Because rotor also will rotate, no? The rotating magnetic field that is sweeping the rotor surface, then you will get the current in the conductor of the rotor. So current carrying conductor placed in a magnetic field. Afterwards, the rotor also start rotating in the direction of the rotating magnetic field. Rotating magnetic field, if it is clockwise, rotor also will rotate in clockwise. That is obvious. But whether the rotor is rotating at the synchronous speed or lesser than the synchronous speed or more than the synchronous speed? Any idea? Why? Why lesser? Very good. Yes. If the rotor, if it is rotating with the synchronous speed itself, how do you get the relative motion between the stator and rotor? Am I right? The rate of change only is inducing the EMF. If the rotor also, if it is rotating with respect to the same speed of the stator, the rotor also, if it is rotating at the synchronous speed, you won't get any relative motion between the stator and rotor. There won't be any rate of change of flux. So no EMF you will get, no current you will get. The rotor will stop rotating. So synchronous speed cannot be equal to the rotor speed, right? But what is making the rotor speed to become lesser than the synchronous speed? See, you cannot make rotor speed similar to the synchronous speed. If you do that, after some period of time, the rotor will stop rotating. But naturally, what makes the rotor speed to become lesser than the synchronous speed? Are you understanding my question? Is that we are maintaining the rotor speed lesser than the synchronous speed? No. Naturally, it is happening. My question is, are you getting? See, you are not making the rotor to rotate at the synchronous speed. If you do that, after some time, the rotor will come to rest. That is a property of the induction motor, right? But what is the natural phenomena is making the rotor speed lesser than the synchronous speed? Anybody can tell me the answer? What makes the speed of the rotor lesser than the synchronous speed? You know or not? You have come very closer to the answer. Very closer to the answer. Very good. Inertia of the rotor. Am I right? See, the rotating magnetic field, no, it is not having any weight. Is that it is having any weight? The flux itself is a hypothetical parameter, right? It is like Atma. Am I right? It is not having any weight. It is weightless. But the rotor, it is not like that. It is having weight. So definitely, naturally, the rotor lags behind the stator speed. The rotor cannot rotate at the same speed as the synchronous speed. It is by naturally, it is like that. See how beautifully they have coined the concept, you see. Yes or no? Yes. Due to the rotor inertia itself, the rotor is not able to rotate as equal to the synchronous speed. Right? So, always you remember in induction motor, rotor speed is not equal to the synchronous speed. Right? So, this one you have to remember. The rotor speed is not equal to the synchronous speed. Due to the inertia, the rotor speed always will be slightly lesser than your stator speed. Purposely, if you make rotor speed equal to the synchronous speed, initially it will run, but after some point of time, the rotor will slowly come to rest. That is what I have written here, right? If NR is equal to NS, relative speed between the stator and rotor becomes 0, induced EMF becomes 0, I is equal to 0, slowly the motor comes to rest. So the synchronous speed will never become equal to the rotor speed. Always your rotor speed will be lesser than your synchronous speed in the case of induction motor. The difference between, right? Now the difference between the synchronous speed and the rotor speed, it is called as slip speed. Okay, it is called as slip speed, and if you divide this ratio by synchronous speed, if you divide this ratio by synchronous speed, this is called as slip of the induction motor. Okay, so generally the slip of the induction motor will be 2% to 5%. Okay, so that is the normal operating value of the slip of any induction motor. Normal operating value I am saying. But what is the minimum value of slip? Hey, minimum, yeah. This is the operating range I am saying. I am asking minimum. Mathematically, I am asking minimum.
0.
Huh? 0. See, this is the working range I am saying. Practically, your slip will be 2% to 5%. But I am asking the ideal minimum value. So, ideally, yes minimum will be 0. Yes maximum will be, what is yes maximum? You tell me in terms of value. Don't tell me in terms of percentage here. 100% means what is the value, man? 1. Yes. Right? So, ideally, the minimum value of slip is 0. And the maximum value of slip is 1. Right? How to arrive this condition? S minimum and S maximum. How you are saying it is 0, it is 1? Why it cannot? See, minimum, okay, automatically you will tell 0. Maximum, how you are saying 1? It can be 2 also, no? Why it cannot be 200%? It cannot be 300%. How to arrive that condition? Any idea? See, you should arrive with respect to rotor speed only, right? When the machine is about to start, what is the value of rotor speed? 0. So when NR is 0, what is the value of slip? 1. So that is maximum, right? When NR becomes equal to NS, that is the maximum speed with which the rotor can rotate, no? More than it cannot rotate, am I right? So when NR becomes equal to NS, what is the maximum value of slip? What is the minimum value of slip? 0. Your slip is coming 0, so you are writing this is minimum. Your slip is coming 1, so you are writing this as maximum. So the ideal range of slip is 0 to 1. But the practical value is 2% to 5%. It means 2% means what is the value? 0.02. Am I right? To 0.05. So 0 is minimum, 1 is maximum, and the operating range is 0.0 to 0.05. So this is your operating range of the slip, right? So practically 0 slip can I get? That is possible practically. You will not get? One slip can I get? Yes. Very good. See, when the machine is about to rotate, right? See, you have given 3-phase input, right? The rotating magnetic field is produced. The motor is just about to start. So during that point of time, your slip is equal to 1. So during the starting of the motor, this is very, very important. So at start, during the starting of the motor, your slip of the motor will be 1 practically. Practically, this 1 is possible. Because your rotor speed will be 0. Okay. But S is equal to 0. This is practically possible or not? No, this will not come practically. Because if slip becomes 0 practically, what will happen to the machine? When the slip becomes 0, it means that your rotor speed is equal to the synchronous speed. The machine will come to rest. So practically, slip is equal to 0. It is not at all possible. Right? So now I will give an example. You have designed a motor for the slip of 0.05 value. Right? You are starting the machine. So what will happen if you plot slip with respect to time? Right? If you plot slip with respect to time, initially the slip will go to 1. Initially, when time t equal to 0, slip will go to 1. Right? Slowly what will happen? After some time, it will come to the design value 0.05. So initially, the slip will be equal to 1 during the start of the machine, but the machine is designed to operate at the slip of 0.05. So after some time, let me take the time t is equal to t1, your slip will come to 0.05. So with the value of slip 0.05, the rotor will rotate. For example, if you take synchronous speed is 3000 RPM. Okay. Your operating slip value, if it is 0.05, at what speed rotor will rotate? Can you tell me? You substitute in the equation, man. S is equal to 0.05. NS is 3000 RPM. What is your NR? Yes. So what you can understand from this, you buy a motor, you start the motor, you measure the slip initially, it shows 1. After some time, because the rotor started rotating, no? So after some time, the rotor speed will come to 2850 for the slip 0.05, because the motor is designed for the operating slip of 0.05. When the synchronous speed is 3000 RPM. When the synchronous speed is 1500 RPM, what is your NR? What is your NR, man? This much time. Yeah, just you divide by 2, man. 1425. Yes. So with that speed, the motor will rotate. Right? So with this, I stop the today's class.